how this works. All right, so yeah, this is gonna be a short story of learning in artificial and natural intelligence. So this is principles of intelligence, not necessarily just artificial. So I'm hoping to get to some natural intelligence at the end of the talk. And there'll be 3 parts, 3 chapters in this story. The first chapter will be about gradients, asking questions like, how does the gradient descent learn features from data? The second chapter will be about groups. What features emerge when neural networks solve algebraic tasks, somewhat related to the last talk on modular addition. And then the last chapter will be about grids. And I'll get into what are grid cells, and I'll hopefully explain some of that. So these are based on 3 different works. The first work was published at NeurIPS last year. The middle work is under review, and the last work is really preliminary results. And this is work done with a lot of authors. Some of the authors in this room, maybe one, Jamie. But really the other 2 who have been leading through this whole last year has been Giovanni Luca Marchetti and Nina Miolaine. Okay, so chapter 1, gradients. In this chapter, I'm gonna try to go through quite quickly because I would like to spend more time on the middle and later chapters. Yeah, just pre-warning, this chapter also will be probably where I lose the most people. So if you get lost, luckily there's other chapters and I'll try to zoom out big picture. So, okay. So we know that neural networks extract meaningful features from their data. This has been an ongoing theme that we've seen in all these talks. I really like, Noah, I like your slide yesterday about this much more than my slide. So I'm gonna at some point borrow that slide. But yeah, we see Gabor filters in the first layer weights. We see meaningful word embeddings, these grokking foray features. At this point, it's pretty clear that part of the reason why neural networks work so well is they are able to extract meaningful features. And we would like to understand exactly what are those features, and can we explain, can we construct kind of a theory of how these features are emerging, how gradient descent is extracting features, ideally showing, being able to explain features we already know, but being able to predict in settings where we don't know what features might come out given a data set. And so before we get into kind of what this work is about, let's just, let's think about an experiment of feature learning to gain some intuition. Jamie showed a version of this in his talk 2 days ago. This is gonna be, I'm basically gonna animate a figure from a pretty famous paper by Shahzad et al. In 2019, which is about this rich and lazy idea. So the experiment is a teacher-student setting. We're gonna have a wide 2-layer student network. This is a 2-layer network with ReLU nonlinearities, takes input in R2, predicts some value in R. And that student is gonna be trained on data generated from a narrow 2-layer teacher network of the same class. But the key idea here is that the teacher is much narrower. It only has 3 neurons. So in this experiment, feature learning is whether or not the student realizes that the data is really actually quite low dimensional in some sense. And if it aligns its student neurons to just the teacher neurons. To visualize this, we'll just visualize this in this kind of R2 to R setting. So here, student neurons will be these blue and red dots. These circles represent kind of the vector of their weights, and the color is like some sign. But don't think about it too much. Don't look at the math. The teacher neurons are these lines, these rays. Again, there's blue and red for the signs, and I'm just kind of showing the direction of these teacher neurons. And you can see, right, there's 3 teacher neurons, but there's like more student neurons. And I'm gonna initialize the students at a certain scale and then run gradient descent on some fixed data set. So this circle where the student neurons are all aligned represents some initialization scale. You can think about that as like, it's like a variance of your random Gaussian initialization. And the experiment we're gonna run, and the experiment in that paper was, how does the initialization scale influence the learning dynamics and the function that the student learns? In particular, the feature learning, right? How does it influence whether or not the student essentially aligns his neurons to the teacher rays? So in one extreme, we'll have this initialization scale be very large. In another extreme, we'll have the initialization scale be very small. And so now these are just some, a couple different samples. and we'll just run this animation of gradient descent learning with the same data set. So let's start by looking at the far right. At the far right, the initialization of the student is very large, and we see pretty much nothing is happening. There's slight movement in the neurons, but essentially the student weights don't really change at all. Meanwhile, on the far left, it looks like nothing is happening at first, but then there's this kind of explosion event where all of a sudden you see these groups of neurons, student neurons, kind of aligned with the same color and aligning themselves at least somewhat to the teacher rays. If we were to look at through training dynamics, or through like loss, the far right curves will look pretty much exponential. The loss will just quickly go to 0. While on the far left, you see like nothing happens, you're on this plateau, and then during these explosion events, there's drops in the loss, followed by potentially smaller plateaus and drops, plateaus and drops. And if you're looking at kind of a change in the neural tangent kernel, or this empirical NTK, you would see that similar story emerges, where basically in the far right, you're in this what's called this lazy regime or a kernel regime, where you're basically at a minimum of the global loss landscape already. And you're fitting your labels, the data generated by the teacher using the random features at initialization. While on the far left, there's this process of feature learning that the data really is low dimensional. And in the curves, in the loss curves, we see that as these kind of periods of plateaus and drops. So this idea about how the initialization scale of a neural network can move you in and out of a feature learning process is well explored in all sorts of different settings. This was in this like kind of finite width toy example, but it's maybe most clearly demonstrated in these infinite width or limiting settings, as Blake talked about in some of his work. And really the intuition to think about is that when you move into a lazy regime or kernel regime, you're effectively initializing your neural network at a global minimum of the training loss. It's kind of a little bit of a weird intuition, but this is why essentially the weights aren't moving very much, and thus you're not actually learning any features. You're finding ways to fit your target by just kind of reweighting what you already have access to. Meanwhile, in this other regime where we're initializing closer and closer to the origin, I'm taking all my parameters and I'm collapsing their initialization scale. The origin itself is a saddle point of the loss landscape. It's a fixed point. If I were to initialize all my parameters at 0, the gradient of any one parameter depends on another, and so the gradients would vanish and I would be at fixed point. But as I get closer, perturbed slightly off that origin, I'm initializing near a saddle and nothing really happens, but then I have these periods of like falling off the saddle. And during that time where I'm trying to find the escape direction from that saddle, that is like, that's a form of feature learning. The directions I escape in are kind of aligned, mean something, and they're aligned with the data in some meaningful way. So this first chapter of the work is about studying this behavior that's sometimes referred to as called saddle-to-saddle dynamics in this vanishing initialization scale. So the idea was first, I think, termed in this 2022 paper studying linear networks, where they said, look, in the vanishing initialization limit, gradient flow goes through a sequence of saddle points in a linear network. And this idea was then explored in a bunch of other settings like ReLU networks, diagonal linear networks, multi-index models, and also kind of studied in more empirical settings like modular addition, or Jamie has a paper on this like ultra-rich regime in a VIT. And the idea here is that the kind of the behavior we see is that there is this plateaus followed by drops in the loss. And the idea is that this sequence of plateaus drops is associated with going from one saddle point to the next. So this first paper, the goal was to construct a theory or an ansatz of what that saddle-to-saddle dynamics process looked like in the vanishing initialization limit for a class of neural networks, in particular just two-layer networks. And the paper is, again, this is where we'll get lost. But the paper has 3 steps. The first idea was like, we're going to look at a class of neural networks and we're going to propose an ansatz for what gradient descent or gradient flow is doing in this limit. That it's going through this stepwise process, and the ansatz is going to look like a alternating maximization followed by minimization process. So you can think about it as saying like, look, gradient flow, that's just initialize somewhere, follow the trajectory of steepest descent. That's what gradient flow trajectory is. this alternating gradient flow idea is I'm going to start at the same point with the same model, but I'm going to optimize the parameters in some interesting alternating way where I first maximize some aspect of the network, then minimize something, and I go back and forth. And the idea is that that trajectory is actually going to give you the same trajectory as gradient descent in this limit. We then show how we could use that ansatz, AGF, to unify a bunch of existing analysis in linear networks, diagonal linear networks, fully connected linear networks, attention-only linear transformers. These are 3 different settings where we've seen where other works, prior works, have studied this saddle-to-saddle behavior, and there's very clear features that are being learned at each of these step drops, whether it be regression coefficients, singular vectors, principal components. And the idea here is that all of this analysis can all be unified under this framework of alternating between maximizing something, minimizing something. And then lastly, where this is going, this is about groups and grids and whatnot, is we took the AGF framework and we looked at that model that Andrei Gromov used when studying modular addition, and we showed that we can get a similar kind of saddle-to-saddle behavior where each step or each drop here is about learning for a frequency in the task. So I'm going to quickly try to give you the high-level intuition about what this alternating thing is, but this is really the part where you could glaze over, and just as long as you get the idea that there is this, AGF is basically this alternating max-min idea. I won't go into the details after this part of the talk. I'll just be using that, basically telling you what are the solutions of this max and min process. So, but to give some intuition about where this is coming from, let's start. Let's do this. So the class of networks we studied, well, maybe any questions right now? We're in chapter 1. We're like 1.2. Okay, cool. All right, so the class of networks we're going to build this ansatz for are 2-layer networks. Networks that can be written as, their input-output map can be written as a sum of the input-output maps for each neuron. Okay? And each neuron will be parameterized by 2 vectors of parameters. Some input encoding vector, W, which takes your input and encodes it into a real value. There'll be some nonlinearity applied to that value. And then it will decode it back into the output space with the vector A. So each neuron, the ith neuron, has 2 vectors, Wi and Ai, and I might just call that theta I from now on. That's just the parameters of the ith neuron. And that nonlinearity we're going to assume is origin passing, meaning sigma of 0 is 0. So linear, square, ReLU, but really, like, to think about this, just think about monomial nonlinearities. Anything that looks like sigma of z is z to some power. The last thing is we're going to initialize the parameters of each neuron as some random Gaussian with some variance alpha. And I'm going to think about, again, we're talking about this rich regime. I'm going to take the initialization variance and make it very small, close to the origin. So there's 2 observations that really are the start of how we build this ansatz, AGF, about this class of networks in this initialization regime. The first observation is that if a neuron is 0, if the neuron's parameters are 0, so if theta of I, A, and W, if all of those parameters are 0, then that neuron is dead, right? It basically, the gradient of W depends on A, gradient of A depends on W, and because the nonlinearity is origin passing, that 0 commutes through, and it means that that neuron won't change through training. The next observation is that 2 neurons are only aware of each other, personifying neurons under gradient descent dynamics. They're only aware of each other through the fact that they share a residual, right? Neurons don't share parameters. So the only way that one neuron's dynamics can be influenced by another neuron's dynamics is that they both are driven by a shared residual that depends on the full function. So that's where 2 neurons end up influencing each other when it comes to gradient descent dynamics. So from these 2 observations, we can make a couple further observations about critical points of the loss landscape of networks of this form. Any critical point of the loss landscape could be described by a partition of my hidden neurons into 2 sets, a dormant set and an active set. The dormant set will be neurons that all the parameters are 0. So these neurons are dead neurons. The active set will be neurons that have non-zero parameters, and they are at a critical point of a restricted loss landscape to just that set of active neurons. That construction of 0 on the dormant neurons, some critical point of a restricted loss landscape of the active neurons, is a critical point of the full loss landscape with all my neurons, right? And so in particular, the origin where all my neurons are dormant and I have no active neurons, that's a critical point of the loss landscape, right? All my neurons are effectively dead, are dormant. And when we initialize with a very small initialization, we're initializing very close to that critical point of the loss landscape. Okay, there's one last maybe critical observation about now we want to study, so with that in mind, we know in this regime I'm initializing close to critical point, the critical point where all my neurons are dormant. We now want to make an observation about the dynamics near these critical points. In particular, let's think about what the residual is. Let's imagine it's mean squared error. It's not necessary, but that's where it makes the most sense, most intuitive. So if the residual is going to be like a difference between a target and my prediction over my network. But notice the prediction of the network is a sum over my neurons, right? And my dormant neurons, they're all 0, so they contribute nothing to the prediction. Which means that my dormant neurons, let's just think about this, or scratch what I just said, let's just take a step back, right? The residual is just a difference between target and the function. The function will only depend on active neurons. It has no dependency on the dormant things, right? So it means that the active neurons, they're all in some equilibrium and influencing each other through that shared residual that they all depend on. And they influence the dormant neurons through that residual that they basically construct. But the dormant neurons, they have no influence on the residual, so they have no influence on each other, right? So near these critical points, the dormant neurons are unaware of each other. Remember that previous observation? They only can be aware of each other through a residual, and if one dormant neuron has no influence on the residual, then another one will not be aware of that dormant neuron. And similarly, the dormant neurons have no influence on the active neurons. So again, kind of personifying what's happening is the dynamics near these saddle points are basically the active neurons are in some equilibrium. The dormant neurons are all going to be independently trying to escape their saddle point. And they're going to do that independently. At some point, one of them will escape, and that will be driving the process to a new saddle point, and there'll be a new residual. And essentially, hopefully you can see the flavor of what this max-min idea is looking like. Basically, it will be like maximizing finding an escape direction over just the dormant piece of the network, then minimizing among the active neurons to get back into equilibrium, and then repeating that process back and forth. So I'm going to kind of go through this very quickly, but yeah, so what we can do is we consider a saddle point where we have an active set, dormant set. We can, this is basically saying what I just said, the residual really only depends on the active set. The dormant neurons are now independently going to be maximizing a utility, which is basically a correlation. This is like the component of their gradient that's driving their dynamics. So there's this utility function, which you can think of as basically a correlation of the dormant neuron with the residual. Basically, how useful is that dormant neuron to fit what's remaining in the task? And there's this interesting thing that there's this separation of timescales where essentially directions move quickly and norms move slowly. And so we can use that to find these optimal escape directions and then solve for the dynamics of just the norm, and we get a nice expression over essentially when does a dormant neuron activate. And then we can figure out, well, what's the first neuron to activate? And I'm skipping through this very quickly because I just want you to get the high-level idea of what this ansatz is saying. So at a high level, this alternating gradient flows idea is saying, look, we start at some saddle point with some active neurons in equilibrium. In the beginning, the active set is empty. We're at the origin. So, of course, the empty set, it's in equilibrium. That set generates a residual. Then the dormant neurons all try to maximize independently their utility with that given residual. They're doing this all independently, and we can basically solve these maximization problems explicitly. We can solve for the direction of maximal utility, and then we can solve for the time it takes for a dormant neuron to activate. we then get the first neuron to activate, basically jumping from essentially near zero parameters to non-zero parameters. At which point we add that dormant neuron in that direction to an active set. The active set is now out of equilibrium, and we need to solve for the new equilibrium of the active set of neurons, and that is this cost minimization step, which is quick with respect to the utility maximization step. So if we look at this through this picture of saddle-to-saddle dynamics, these plateaus, drops, each of these phases in this loss plot are associated with these two optimizations that are alternating. Maximization is this slow step on each of the plateaus, and the minimization is this fast step. And with each of these steps, we have neurons going from some set of neurons or one neuron going from dormant to active. And we keep doing this until either we fit the target or we have no more neurons that are dormant. And then at which point it's done. And there's an asterisk here, which is what I'm not going to get into, but actually sometimes active neurons can go back to dormancy. So this is kind of a weird thing, and it happens, and there are examples where that can happen.
So is it the case in the plateau phase that the escape is always associated with the new direction?
Yes. You're saying, could it be that another neuron escapes in the same direction as a previous neuron? Yeah. So
like early phase where all the directions are neuron that then being chalked out of don't necessarily have like a new direction.
So what often happens in the problems we study is that there'll be multiple neurons all activating in the same direction. So it'll be more like a population of neurons activating in a certain direction. And that's, yeah. And when it comes to how do we use this idea to do analysis, we're basically, another way to think about what we're saying is, in this vanishing initialization limit, we can deconstruct or gradient flow as these alternating, optimization problems. So and each of these optimization problems is simpler than solving the full gradient flow dynamics. And so in the problems we study, there are usually analytical solutions to each of these optimization problems, and that's how we're using it to construct, we're like stitching together the smooth gradient flow trajectory as a alternating like optimization problems. And so yeah, in many of these cases, the optimization problems directions are always orthogonal to the previous ones, which really helps when it comes to analysis. In general, that's probably not the case. Yeah. Yeah.
Can you say the
Yeah, it's literally the correlation of that neuron's input-output map with the residual, taking the expectation of that over your inputs. So it's basically saying how useful it's the first order Taylor expansion of essentially the loss with respect to that, or of the gradient with respect to that neuron. It is basically just saying I want that neuron is driven mostly by trying to find a direction that is maximally overlapping with the current residual. Yeah. Yeah, Will.
So actually none of the dynamics for the utility maximization step, or can you just pick the direction that will maximize?
Yeah, so when it comes to the analysis, we can pick the direction. And this comes to the separation of timescales, where if you essentially choose the learning rate correctly, and that means, it has something to do with essentially if you make the learning rate dependent on the norm for arbitrary nonlinearities, or just in certain cases. But yeah, basically there's this separation of timescales where the direction is effectively instantaneous in the vanishing initialization limit. So you can just solve that constrained optimization problem, at which point now neurons will be in different directions and they'll be growing at different rates. And so then you can just figure out, which neuron is going to escape first. And the very interesting thing is that the utility step of maybe the third step actually depended on the utility steps of the first and the second. So it isn't like fully Markovian at everything, or, it actually depends on the sequence of steps you've done before. But yeah, from the analysis point of view, that's exactly where we're going to get how do these Fourier features emerge? There are going to be solutions to these constrained optimization problems. Okay, so yeah, I prefaced this idea earlier, but basically you can use this to unify a bunch of existing ideas in linear networks. Maybe to give a good example of what this utility function would look like, in the case of a fully connected linear network, the utility of a neuron, in those cases, your data ends up looking like some sigma yx, which is in the input-output space. And the utility of a neuron, remember it's two vectors, wi, ai, ends up looking kind of like ai transpose sigma yx wi, right? And so this utility maximization phase looks like maximize over ai equals wi equals 1 in norm, this quantity. And anyone know what this kind of maximization problem looks like? It's this bilinear, I mean, my handwriting is bad and it's small, but it's a bilinear, you have a matrix of your data, sigma yx, and you're having an inner product with that with your two vectors, and you're saying maximize that inner product subject to the norms of those parameters being fixed. So you'll align to the top singular value vectors of sigma yx. So like this utility maximization phase gets you aligned to these singular vectors, the top one. And at the next step, I said it depends on the previous ones. Well, this sigma yx ends up, you subtract that aspect of the task from it, at which point you have like a modified sigma yx with one less singular value, and then you go to the next top singular vector. So you get this kind of behavior.
So I have a question first. In the normal GT theory for linear networks, that these directions are they're like part of what, that they don't depend on the initialization pair, and that you don't need to wait in the phase of platoons for the directions to be.
I'm sorry, in which?
Like in GD, not.
In GD, like for linear networks, it depends on if you're task aligned initialization, and that's what they do. They basically already align to the things.
It be very, very quick alignment, and that these platoons only correspond to like the singular value movement.
And the rate at which these occur are according to the singular value. Yeah. So it's the same. It's literally the exact same in that case. Okay, I want to keep moving on. So again, we looked at how, okay, great, it unifies a bunch of things we already know about. What about, could we use it to try to explain the dynamics of a setting where we know this final solution, but we don't necessarily know the trajectory of how it got to that final solution? So we looked at modular addition. In particular, we looked at that setting, and I'm going to skip through the setup here pretty quick. Modular addition, p squared inputs, they're all one hot encoded. You have this 2-layer quadratic network, takes 2 of these vectors, predicts a vector, and we're using the model that Andrei Gromov used because there's this, like you said, there's this quadratic nonlinearity, and interestingly, each neuron ends up aligning its vectors to being a wave with a certain frequency. And if we were to like look at that through training, just to give some idea, what happens is first, like the neural network predicts the mean of the one hot vector, and then it goes through this like wishy-washy phase that maybe looks like saddle to saddle if you squint. And the neurons do really pop up aligned to certain different frequencies. So we were like, maybe this could work. Maybe we could try this. And then we realized something kind of interesting, which was, why did we encode the input as one hot vectors, right? That was a choice. We have, remember, the inputs are integers from 0 to p-1, and we decided we'll encode those as one hot vectors in RP. And one way to think about what that one hot vector is I take the E0 vector, just the one where I like 1 and then all zeros, and I shift it by k times to represent the kth integer. So that's the one hot vector. That's one way to think about what a one hot encoding is of a bunch of integers. It's a cyclic shift of a fixed base vector. So what happens if we took a different base vector and cyclically shifted that base vector to construct a encoding of my integers? When we train with that, kind of weird encoding, suddenly there wasn't just a wishy-washy phase of saddles and whatnot. Now there was a specific ordering to what Fourier features were learned and at what time and in what order. And it was, you randomly initialize in a new way and you would get the same ordering. Assuming, and there's a really kind of natural hypothesis then of what's going on here. We know the features are Fourier features, that's the right basis, as was said in the last talk. And if you look at it, one hot vector in the Fourier domain, it's uniform in the Fourier domain, meaning all powers are equally important to producing a one hot vector, right? Meanwhile, if I took a vector that is has a non-uniform Fourier domain, well, suddenly there's some directions that are more important than others. And so this would be like, imagine you were training a linear network on orthogonal data. All directions are equally likely. There would be no preference to learning one singular vector over another because all singular values are 1. And so that was the hypothesis, is that the learning is going to be dictated by the power of the Fourier coefficient with respect to the way in which we encode the task. And indeed, if we then applied our analysis of AGF, we say, okay, well, what's the utility maximization phase? And you get this constrained optimization where you try to find these directions of maximal alignment with the residual subject to a norm. You rewrite it in the Fourier domain, and you get this convex optimization that you can solve. And in fact, yeah, the cosine waves align to the dominant frequency of the way in which you encoded the task. That's the optimal escape direction. The cost minimization phase, once you have neurons in that direction, how do you minimize the loss in that direction, is a lot more complicated, but still within the subspace of kind of neurons aligned to a single frequency, you can find that there is a lower bound, and that lower bound is achievable if you have at least 6 neurons aligned and they distribute their phase shifts. And so basically what we do is okay, great, we have this back and forth, and nicely when you actually achieve that lower bound and repeat, the whole thing becomes recursive. So what happens is essentially you're repeating the task with one Fourier frequency removed. So just to give you like an idea of what the theory would predict is, in the beginning, you're on a plateau at the origin, and your weights are all kind of randomly aligned to different frequencies. So this is showing each line is a different weight, and that's kind of its frequency or its maximum frequency. And then there's a point when there's a sudden drop where a group of neurons will align to the dominant frequency of my encoding vector, and then they'll distribute their phase shifts in order to basically remove that frequency from the task. And then it will repeat with the next dominant frequency, and so on. And so if you were to look at this in terms of that was kind of showing you in terms of just the parameters. If you were to look at this in terms of the prediction or the way in which the network, like what the network is predicting. On the right, I'm showing you for a fixed example of, A is 1 and B is 4. This is like my 2 inputs. The blue curve is the true target that the network is trying to predict. The black curve is what the network actually predicts, nothing, 0. And after that first drop, it's learning to predict the target, but using only a single frequency. And then with the next drop, it learns to predict the target using 2 frequencies, and then eventually 3, and that, in this case, there's only 3, and that's why it interpolates. So there's this nice picture emerging so chapter 1 is, I hope, done. So it's basically, in this vanishing, we want to understand how gradient descent picks out features in data. It's a complicated thing. A good answer to this would basically be like, massive, but we don't know how to do it. We looked at a very restricted class, but still interesting class, 2-layer networks with nonlinearities that are origin passing. And we onslotted that in this vanishing init limit, there is this implicit alternating min-max optimization that could explain how the features are emerging, unifies some things, and explains why Fourier features emerged. And there's lots of things to go from here. Like, in general, this stepwise behavior isn't always seen. Why is that? Is it because there are many steps, small steps, that lead to some smooth decay? Or maybe these cost min steps that we assume are really quick are bleeding together, breaking some of the assumptions of the analysis? My guess is both are true. It is in ansatz, and in only one setting, diagonal linear networks, can we prove that this ansatz is true. So, or is there another set of settings where we could prove it? Can we connect it to more classic analysis in multi-index, teacher-student? I would be very interested in, could we make this description that is kind of discrete, something that might look more smooth, where you have kernels and kind of low rank perturbations to that kernel, So I think there's lots of different directions, but maybe most importantly, what would this look like in a deeper network? So all these are important, and none of them are done. So chapter 2, groups. So we were like, okay, modular addition, that was cool, 4 features. What's the generalization of this idea to a more complex setting where we might expect our analysis to still hold? So modular addition can be seen as essentially group composition with a cyclic group, right? Groups are sets with an operation and some other properties of that operation. And so in this case, the A plus B mod P, that's the group composition rule, and the different, A and B, these are the elements of the group. So the generalization of this would be, imagine I give you a sequence of elements from a group, and I ask you to learn the composition rule of that sequence of elements. So that's what we're calling this sequential group composition task. So this visual depiction here is every configuration of a Rubik's Cube is an element of a group, of the Rubik's Cube group. And so imagine I gave you, and you could think of them, each configuration as essentially a movement, an operation. So I could give you a bunch of these operations and ask, well, what's the composition of all those operations?
It's like you're just relaxing the saying that it's not the win anymore, basically.
We're relaxing the cyclic group to any group, abelian or non-abelian, yeah. And then we're going from 2 inputs to k inputs, and that's it. Okay. Yeah. So that's the generalization, and then we'd ask, okay, how would neural networks learn? Can we take our analysis and figure it out using something similar to what we already did? Okay, so zooming out, what's the task? Okay, chapter 1 was about a description of a feature learning process that involves breaking things up into max and min steps, right? Chapter 2 is about a class of problems that's slightly more general than the class we studied before and that we think might have interesting behavior. So this task is, given a finite group, train a neural network that maps k elements of the group to the composition of those k elements. We're going to encode each element of the group as some vector, kind of foreshadowing here. Similar to what we did before, there'll be a template vector with some mapping, some permutation of that vector to represent the different elements of the group. We'll study at first 2-layer networks, but then we'll also look at what happens if I move to RNNs or deep MLPs. And then lastly, we'll be using this AGF idea when we study the 2-layer networks, and then just kind of trying to extrapolate what we think is going on in RNNs by creating constructions rather than dynamical analysis. Okay, so that's this is the sequential group composition idea. Okay, so really quickly, there's some really nice properties that come out when you study this task. First, this task is interesting because it's compositional, right? It depends on all of your input, and you're actually trying to compose those inputs together. Kind of a natural task, and I'll get into that in a second. The task depends on 2 critical factors: the form of the group G and the statistics of how we encode the elements of the group. It requires a nonlinear architecture to learn. So we can prove that a linear network will never be able to learn this task. And similar to the Andrei Gromov paper of what's the minimal architecture that can do it, it will be a 2-layer network with polynomial nonlinearity. It has a similar story of feature learning where you learn things one at a time in some order. And that's going to be, instead of the Fourier frequencies as cosine waves, it's going to be the irreducible representations of the group. There'll be a provable benefit of depth as the sequence length grows. Essentially, as the sequence length gets longer, 2-layer networks will need exponentially wider hidden width, while deeper networks will find efficient kind of roundabouts. And lastly, there's kind of a nice extension of how to take this algebraic task of group composition and start moving up into more complex tasks that are no longer described by groups, but could be described by semigroups, for example. It's essentially similar algebra, but you're removing some of the properties of groups like invertibility. And these look like finite state automata or some stuff like this. Yeah. Okay, I in some sense, this slide covers the next everything then like I'm just gonna go through each of these points. So maybe in the interest of time, what would people like to? Yeah, no, I will choose. Okay. Okay. I think what we'll do is we'll skip. I don't really know what these. Okay, yeah. So just again, there's three choices, right? It's the group. It could be abelian, non-abelian, meaning it's order sensitive, order insensitive. It will be how we encode the elements of the group. It will play a huge role in what's essentially the order of events. And it's the sequence length k. How long is that sequence length? So these three choices of the task will have big impact on the learning. We're going to skip. Okay. First, we can show that a linear network can't learn the task, but the minimal network that can learn it is essentially this two-layer network where the polynomial is z to the k, where k is the length of the sequence. So remember, in the quadratic case, it was k was 2. Sorry, in the two modular addition case, k was 2. Well, if you have 3 items, k will be 3. And you might think, okay, you asked earlier, like that's a weird why. Well, interestingly, like if I were to train with like tanh or gelu or relu, this behavior, you could think about just Taylor expanding that nonlinearity near the origin, and that would tell you something about whether or not that nonlinearity can learn it or not. So for example, tanh is odd, meaning it has no quadratic term near the origin. And indeed, tanh does not learn through this similar stepwise process as square. It actually learns through something totally different. It does learn it, but in the beginning, if you were only to train to a fixed amount of time, it would not learn the task. However, it's cubic, it does have a cubic expansion, and so in the k equals 3 case, it does learn it, and it does learn through this stepwise process. So, why quadratic, why these things? I mean, really, it's for the analysis, but it seems like other nonlinearities, you can Taylor expand them and get pretty good predictions of what you would expect to happen. But yeah, so another way to say this is, whatever this is completely different strategy than what we are describing in the monomial case. Okay, I'm just this slide. What changes in our analysis? If you're familiar with groups, every group has its own Fourier transform. So we go from essentially the classic Fourier transform of sums over cosine waves to sums over what are called irreducible representations. We move from quadratic to k equal to monomial of k. You get a similar idea that utility maximization is about aligning neurons to dominant irreps. Cost minimization, you get another thing. Remember I said 6, that was weird. Why exactly 6? But there's, again, a minimal width that you need, a minimal number of neurons to learn each irrep. And that minimal number is actually going to be exponential in k. But otherwise, the same behavior. This is different groups, abelian or non-abelian, and really you get this similar behavior. Our analysis, again, is in this vanishing init limit, and there are assumptions, but it seems to track relatively well what we think is happening. Okay, yeah, this exponential thing is weird, right? Two-layer networks, as k grows, become terrible. And really, there's a really natural way to see what's happening. What the network really wants access to is a term that looks like a product of activations. But what it gets access to is a sum of activations squared or to the k. So what you're basically finding is that this exponential thing comes from the fact that, let's say I have two values, z1 and z2, and I want to get their product, but I only have access to z1 plus or minus z2 squared. Well, if I had 2 of these things, I could, interact them to essentially cancel all the other terms and leave just the activation, the term I care about, the cross term. And as you expand this to k, this is a similar idea, but you'll need there's a similar decomposition. This is called this Waring decomposition, but you'll need this exponential number of different interacting pieces. And so we can show that, so we can get a lower, or essentially a lower bound on what we think the minimal width of a two-layer network is as a function of k. And what I'm showing you here is the training loss at convergence. Red means it didn't learn. Blue means it did learn. And I'm looking at changing the group size and the hidden dimension for different lengths of K. So as in the beginning, it's like, okay, yeah, with 6 neurons per EREP, I can learn it. But now I need maybe like 12. And then maybe here I need 36. And over here I need like 100. I don't know, actually. But this is the value that you would need. And you can see that that's this black line here. And as K gets bigger, that black line goes up quite a bit and indeed seems to track what we find empirically. So it's tracking that above that black line, the network can learn it. Below that black line, the network can't. In the middle, around the black line, it can do some stuff.
This is a certain understand.
This was a cyclic group, yeah. Okay, so then you would ask, well, could the deeper network find more efficient solutions? And indeed, there's a really natural way to think about how deeper networks could find more efficient solutions. We're not going to dynamically show that. We can't, because AGF was restricted to 2 layers. But what we can do is construct solutions using our solution to the 2-layer network and show that indeed gradient descent seems to find those solutions, not fully empirically tested, but at the very least, this is a construction that demonstrates that a deeper network has the ability to learn a more efficient solution than a 2-layer network. And it really just leverages the fact that this task is compositional. So in RNN, for example, if it's given the sequence of elements of its group, all it needs to do is learn to compose them G1 with G2, compose that with G3, and so on and so forth. And in doing so, it can keep its hidden width as wide as what it needs for the binary task. A deep MLP can do something similar that's discussed in literature, where it basically it can parallelize this thing and break up the tasks kind of in parallel, composing adjacent pairs and doing a divide and conquer. So with log K layers, where K is the sequence length, it will have this ability to, again, keep its total number of hidden neurons kind of in the order of what the binary task would have been.
But progress is exponential K.
Exponential in K time? Oh yeah, you mean like just because you're still training?
That's far.
Oh, okay, so this is I think what you're getting at, there's still an important point here, which is all of this stuff, and maybe I should have said this earlier, is about population loss. We're not thinking about generalization. When I got interested in this grokking, task, this modular addition task to me was interesting for 2 reasons. Sure, the grokking aspect is quite interesting, but I was also just like, why 4A features? So in these things, this is a construction. We don't know anything about, we're not saying anything about sample complexity.
Even at population loss, it takes and
We're not talking about dynamics in this, we're talking about constructions. Okay, I do want to get to grids, even though that seems impossible, but I do want to get there. So the point of this is just saying, yeah, there is a natural way that these networks could learn to compose things using their depth to get more efficient. And one of the kind of interesting consequences of this construction would be that, for example, the mixing matrix in an RNN would end up block diagonalizing, where each block would be a different EREP. And so if you actually train these networks with gradient descent and you look at that middle matrix and you just look at it through training, it looks like kind of noisy and then it kind of, I don't know, something happens. But if you if you permute the elements of that matrix according to the alignment of the output neurons in their 4A domain, you find that really there are these blocks emerging where the RNN is essentially, through training, the gradient descent has kind of split the RNN into different RNNs, each associated with one irreducible representation of the task. This is just saying that same thing through training. The output layers are aligning in some sense to irreducible representations. In this case, it's the cyclic group squared, so these EREPs look like 2D cosine waves, and the RNN is kind of block diagonalizing. Okay. Chapter 3.
You have -1 minute.
-1 minute. That is exactly how much I prepared. Okay. This is natural. This is the natural intelligence. Also, I think this is fun. There's some like Arctic explorers in this. All right. Animals live in space, and so survival depends on navigating it. Okay, what? So, woo, pivot. We're gonna see navigation and algebra, algebraic tasks are somehow related. In 1873, Charles Darwin wrote to Nature about animal navigation. He read this guy's book, von Wrangel. There's an island in northeastern Siberia called Wrangel Island, where the last population of mammoths, by the way, were found. They lived to 2000 BC, so 4,000 years ago. There were 6 mammoths 10,000 years ago that ended up on that island, and they just were like incubating themselves until eventually their demise. 6,000 years past the rest of mammoths. So when, think about how crazy that is. Only 4,000 years ago, there were mammoths on that island. Anyways. Von Wrangel wrote about his adventures in the Arctic area, traveling the ice, and Charles Darwin read that, and he noted, "We must bear in mind that neither a compass nor the North Star nor any other such sign suffices to guide a man to a particular spot through an intricate country or through hummocky ice. When many deviations from a straight course are inevitable, unless the deviations are allowed for and a sort of dead reckoning is kept, this leads me to the suspicion that some part of our brain is specialized to the function of direction." So he read about this guy's journeys through essentially nothing, like white ice, that was all complicated, and yet the Inuit guides that he was working with could still navigate through this and remember how to get home after hunting for seals. And he said, hey, there should be some part of our brain. And this ability to dead reckon soon came to be understood as a form of path integration, that animals have this ability that kind of given, internal signals of their own self-motion, whether it be from our, visual or motion cues, we're able to kind of estimate our global position or allocentric position by integrating these egocentric movements. And then in the 70s and to now, we've developed the experimental tools to start to uncover that neural basis of this ability. So literally, rats moving around an arena, things on their head recording neurons in different parts of the brain, hippocampus, entorhinal cortex. And we record these neurons and we find that there's these cells that activate with these unique patterns. So cells that activate whenever the rat is in a certain place in the arena, or cells that activate when the rat is near the borders of the arena, or cells that activate in these kind of band-like waves across the arena, or cells that activate in this weird hexagonal grid structure within the arena. And these grid cells came to be understood as kind of you could think of them as internal GPS coordinates for the rat. And there's some really interesting phenomena. I'm not an expert in this at all. Will is, but there are these hexagonal grid cells. They're tuned in this way where they basically, it's as if there's a hexagonal coordinate system over the arena. They come up in this modular structure with different modules of different resolutions. There is some interesting behavior now about how these things are learned through development, whether they're there hard-coded, what aspects are hard-coded from evolution and what part are learned through the rat's own exploration. And there are these cells that have this kind of conjunctive, both hexagonal tuning and kind of the direction that the rat is facing tuning. And there's lots of different models. I mean, there's a lot of different excitement about how to describe this over the last, since 2005 when they were discovered. There's these models that are attractor network based, that would kind of hard-coded, hand-designed, that describe how these circuits could emerge, or how these circuits could be stable and give rise to this behavior of navigation. There are these ones that are kind of more normative, just basically why is this optimal? Circle packing in 2D, this kind of idea. And there are this task-driven kind of ideas where you just take a neural network and you train it on an equivalent task and see that these features emerge. And I'm just going to give you the gist of it. The idea here is we think of path integration abstractly really is sequential group composition. Integrating a sequence of group compositions. That group is going to be the group of all rigid body motion in 2D, this SE2. And this group has kind of interesting behavior. In particular, the irreducible representations of this group in 2D actually are hexagonal waves, hexagonal lattices with different resolutions. And in 3D, you get weird lattices. I mean, things that I don't really know how to describe. And indeed, if we train our RNNs on these sequential group composition tasks, but using a discretization of that SE2 group, we find that the weights do end up you find neurons that are selective in the arena to things that look somewhat like grid cells. I'm going to just zoom out now. My research is about trying to understand the mathematical principles governing learning in artificial and natural intelligence. And I think that by studying these vanishing initialization regime with interesting structured data sets, we can gain insight about how neural networks learn features. And I hope that we can use those insights to build theories for learning in natural intelligence, really treating the neural network as a model organism of intelligence. And while it's quite different from mammalian intelligence, it might be sharing the same underlying physics of learning. So yeah, that's story end. Thanks.